isothermal processes and adiabatic processes, constant volume, constant pressure processes, that's when it's gonna come back. And these are also standard ones that if you pursue thermodynamics of any sort, that this is just the terminology that will be used so that you can go, oh, wait a second, no one's seen that before. All right. Isochoric. And we sort of hit this one already. We have the thermal energy is equal to Q plus W, and just first law of thermodynamics. But if volume is constant, so delta V equals 0. There's no work being done. If the volume's not changing, there is no displacement. No work is done. And so we just have that any change in thermal energy comes from this change in Q. Isobaric. Which means
pressure is held constant.
yeah. I think I misspoke earlier. I said that Michael Jackson supposedly in an isobaric chamber. I think he had a hyperbaric chamber. So he slept under greater pressure or less, whatever it's supposed to help you.
I think it's higher pressure.
Yep. Okay. I guess there's hypobaric and hyperbaric.
I think so, yeah.
Do you think Michael Jackson slept under greater pressure? Or you were just addressing hyperbaric means?
I would hope it was greater pressure. I feel like less pressure.
I guess you run the risk of the bends if you do that.
Yeah.
And who knows how much of any of the rumors on Michael Jackson were true. I believe you even had a song about that. All right. So the total work that's being done just P delta V. We sort of looked at that before, the PV process, or the PV diagram. Pressure is constant, it's just the area underneath the line segment right there. So that's negative, which version am I using here? I'm using the physics version. In KB T over V delta V. And we have to specify that better. V final minus the V initial. Oh. This would be, I guess whichever one we do. I mean, this is, because I have changing volume here, and so which volume do we pick? So I guess if this is the final temperature, that's the final volume. If that's initial temperature, it's the initial volume. So it should also be equal to N kBT initial over V initial, V final minus V initial. And then it's just the math, distribute the VF through, so we get negative N kBT final 1 minus VI over VF. And down here, negative N kBT I times VF over VI minus 1. It's just math manipulation. Just a couple more specific processes, then we'll get into, hopefully, a use for them. Free expansion is another specific process. It's probably the simplest of them all. In free expansion, you have a gas that has no limits on it. If there are no limits on it, that means that there's nothing being added to it. It's not interacting with anything. It is just floating out there, infinite into the infinite volume of space. It's not doing any work. There's no exchange with any external source. In essence, it is the simplest and most boring of all of them. And then the last bit. Then we'll take a break and then we'll start applying some stuff. The cyclic process. Look at the PV diagram again. Go from here to here, and then to here, and then to here. We basically have a process where we end up back where we started. I know that the work done here, this is the work done by the system, or the negative of the work done by the system. This is the work done on the system, or the negative of the negative going the other direction. In essence, I've got one process moving to the right, the other process is moving to the left. The total work that is being done is the area in between. So the total work is just the area between the two processes. So I guess it would be integral from, if this is V1 to V2, I'll call this path 1, call this path 2. So the integral along path 1 of V1 to V2 of PV plus the integral from V2 to V1 along path 2. But the main thing I want to get out of this is the fact that the area in between these two is the total work that's being done. And that is something that we will exploit before the end of class today. All right, when we come back, we're going to look at a specific process here, taking advantage of some of these ideals that we just did. The energy transfer diagram. See the right order. Times. We'll have P and V. We're going to start out at some state where we have some initial pressure and volume. I'll call this point A. we're going to then do an isochoric change, or isochoric process to go to point B here at a higher pressure. Then we'll do an adiabatic expansion. Then we will shrink the volume, and then we'll do an adiabatic compression. So this is an adiabatic expansion. Adiabatic compression. And we'll figure out how much work was done. All right, let's take a small little break here, stretch legs. All right, so taking a look at this particular process here. We start out, imagine that you have a gas inside a piston or inside a cylinder with a piston on top. You're putting heat into it, so heat's coming from some high temperature spot, at least at a higher temperature than the gas. Pumping energy into it, piston is not moving because the change in volume is 0. So as you put energy into the system here, the particles should be moving around faster, and so there's going to be a higher pressure is building up. So that's this process right here. Then, during the second phase, that pressure, the piston is released so that the piston can move, and the pressure moves it up. So there's work done by the system on the piston. So work is coming out of the system. We now have, with the piston up here, there's going to be a transfer of energy because of thermal differences to something else as we pull energy, thermal energy out. And then with the lower temperature or the less energy in there, there's less pressure, the piston's allowed to come back down and work is done on the system. So that is what's happening in this diagram right here. I know that in when the volume is constant, the isochoric process, that no work is being done. So the change in thermal energy is just the heat being put in. In the second phase, work is being done by the system, and so work is leaving this environment. And so this is going to be negative, work out. So this is a change in thermal energy of the system. This last phase, we are losing energy through QC. And then work is being done on the system. So the change in thermal energy would just be the sum in all these processes. So for this particular system, the change in thermal energy is going to be QH minus work out minus Q to the cold region plus work in. And since we ended up back where we started, if we assume rate efficiency here, ultimately we're back where we started. There's no change in thermal energy overall. Whatever we took out, we put back in, or whatever we took in, we put back out. And so we have work in minus work out is equal to the energy being put in minus the energy, thermal energy being put in, heat in minus the heat out. This is just a nice simplified ideal situation. This work in minus work out, this is the work of the engine. And it's equal to the change in the difference in the heat in and heat out. The one thing that the book does is they define QC to be the energy that's leaving. But it can get confusing that if I have energy leaving from the system's point of view, it's negative, that it would be a negative number, but they aren't looking at it from that point of view. They have if you want to keep QC negative, this would be plus. But what they've done is, don't worry about the negative sign, just subtract. We're looking for the difference in the magnitudes. Now, when you're looking at the efficiency of an engine, efficiency because E is not used enough, is equal to basically work done by engine over the energy in. Let's make sure I get the wording right. Energy out over energy in. So it's 100% efficient if you get out what you put in. Reality is, it won't be. The question is, how close can you get efficiency up to 1 or 100%? So in this particular case, the energy coming out of the system is basically the work done by it, which is going to end up being QH minus this absolute value of QC, divided by the energy you're putting in. Just 1 minus QC QH. So it's 100% efficient if you don't lose any of the thermal energy here. That energy is converted, since we end up back where we started. If this is 0, the only way that that could be 0 and we end up back where we started is if this worked out, basically use all of that energy. All right, next step. We'll get a specific cycle known as the Carnot cycle. The idealized, oh, it's another idealized version. We'll get our PV diagram here. We start out at some pressure and volume. We have an isothermal expansion. That's point A to point B. This is isothermal. And then we have an adiabatic expansion. And then we have point D, isothermal compression. And the last little bit here, an adiabatic compression. using our gas cylinder analogy here. Call that 1, 2, 3, and 4. And process 1. We have an expansion, the volume is going to change, the temperature is not because it's isothermal. And so we have QH coming in, and we have work coming out. In number 2, with the adiabatic expansion, we've done something that's very similar to when we did it over there. We just have work being done. And no energy flowing in because of differences, no heat. In step 3, we have gas compression, isothermal. And so my piston is now falling. So work in, and it's also losing temperature. And then the last step, the adiabatic compression, so step 4, the piston is still going down, so we still have this additional work in. I guess I should differentiate these, they're not necessarily the same. We'll call that 1, 2, 3, and 4. All right, so let's figure out what the total work being done is. Or what ultimately, what's the efficiency? So in the first section right here, so from A to B, it's isothermal. There is no change in the E thermal and the thermal energy. So work done on the system is equal to the negative of the heat flow. So that would be, this is the work done by the system, so work out 1